In today's lecture, we're going to talk about biomechanics and the property of each material. We're going to look at Hooke's law, Young's modulus, tensile strength, and flexural rigidity. First, we're going to talk about Hooke's law and how about the spring is a force of proportional to extension. Let's imagine, can look at this diagram, okay? Let's imagine this is a plane surface and this here is a spring, okay, in its rest position. So the initial length of this spring in the rest position is 0. The x-axis, we're going to look at the extension or the length of the spring when the force is applied to it. Now, let's assume we put a weight or a force, we applied some force to the spring right here. The spring will act and stretches or extends and moves backwards to its original place. This movement of the spring from its initial length to a new length or a new extension, and when applied the force, okay? So the force of x is the force of the rest position or in the initial length where there is no force applied to the spring, okay? In its natural, let's say its natural position. And the f of x is when applied. It means f of applied force. K of s is a spring constant, okay? It's a value that each metal spring have, whether the spring is dense or the spring is loose, like the slinky toy. The law of the force at rest position equals negative the constant by the extension. To explain further why we have the negative in this law, okay, since we have the spring in the rest position, it's when the force is 0 is applied, okay, so the force is 0. However, when there is force applied to the spring, by the nature of the coiling of the spring will move back, will move forward to have new extension, and to return to the original place of the spring, it will move backwards to its original place. So if we want to know, let's imagine that the x-axis is the linear of numbers. So of course, on the right will be the positive numbers, positive numerals. On the left will be the negative numerals. Now, when the spring moves to its original place, it will move to the left side. When it moves to the left side, in numerals, it will take a negative form. That's why the force of rest or in the rest position is in the negative form, because when the spring stretches, it moves to the right direction. Right direction on the linear of number is positive value. However, on the left is negative value. So you can imagine when the spring is stretching and going back and forth, following the nature of coiling of the spring, it will return back to its original place. Okay? When the spring finally returns back to its original resting position, when the initial length is 0, the value of it will become in negative form, because to reach the original state of the spring, it will have to move to the left side. The left side means the negative form or the negative value in the linear of numbers. However, when the force applied is in the positive form, it follows the same rule, okay? Force applied to the spring, it means that the spring will stretches and moves all the way to the right. When it moves all the way to the right, following the linear of numbers, to the right is a positive form of numbers, okay? And when it finally stops and it reaches its resting point, the initial length will be 0, and the force applied also will be 0. Hooke's law for an ideal spring. Applied force needed to extend a spring is proportional to extension. Okay, so the force applied equals the constant of x, or the extension, and the force of rest equals the force of extension equals negative constant by the extension. Okay. From this diagram, we can understand. You can look at the y-axis. You have the applied force, and the x-axis. You can look at the extension or the length. It says here the applied force needed to extend the spring is proportional to extension. It means the more applied force you put on a spring, the further extension the spring will move, okay? Because they have a linear relationship and they are proportional to each other, as you can see in this diagram. This is imaginative diagram of how the molecule bonds a proximate vibrating spring, okay? You can see that the molecule, this is in the resting state. This is when the applied, you can see right here on the left, applied force to the spring, so it extends a bit more. And in the final one, okay, it applies force to both sides. The spring constant K is a measure of the stiffness of the spring, and is a gradient of the applied force versus extension graft. Which means this paragraph, it means that the constant will measure the stiffness of the spring, whether the spring is stiff and rigid and won't extend because of the retention of it, or it's very loose. The coils of the spring is very loose, okay, and it's the gradient of the applied force versus the extension graph. You have here the gradient equals the rise divided by the run, or the up divided by the along. The gradient equals the constant, which equals delta force, or delta over delta the extension. We can look for further explanation through this paragraph. Again, the y-axis is the applied force along the x-axis, which is the extension. So let's say a spring was applied a force to upon, okay, and it stretches. When it stretches, it will move back and forth multiple times before returning to the original place. So we will have an initial extension, which is the x1, that will be proportional to the initial force applied, that is F1. While it's continuously moving, we will have another extension, okay, which is the x2, that will be proportional to the second force applied, which is the F2. Now, to know what the, of course, every metal or every spring have a constant of its own. To know the value of this constant, we have to divide the force applied over the extension, or you can call it also the length. To know this value, we have to know the value of delta F, or delta force, by summation or subtracting the second force minus the first force. We're going to know the delta F. And to know the value of delta X is by subtraction of the second force minus the the second extension minus the first extension. You can see here in the note, this triangular sign means delta, And delta is the change or difference, okay? To know the delta, or you can also call it the average, by subtraction of the second force by the first force. So, you have this question here. If a force of 10 Newton extends a spring fixed on one end by 5 centimeters, then what is the spring constant? As you can see here in this in this question, what they want is the spring constant. If we go back to this rule of the spring constant is by dividing the force over the extension. We have here the force of 10 Newton. We're going to divide it by the extension, which is 5 centimeters. Okay? Sometimes instead of using the word extension in the question, they might use the word length, which is the exact same meaning because it is the measurement that the spring will move. So it has the same meaning. Okay? So a force of 10 Newton extends a spring fixed at one end by 5 centimeters. Then what is the spring end? To solve this question, you can say K, which is the constant, equals the force divided by the extension, which is 10 divided by 5, which equals 2. If the spring is ideal, obeys Hooke's law. We can go back to look at Hooke's law, which is this one. Okay? What force is needed to extend the spring by 10 centimeters? Let's assume the spring is ideal. Okay? And then we have the extension. By going back to the law of Hooke, is F at rest equals negative the constant by the extension. Let's assume the constant of this spring is the same constant of the spring in question 1. So it will be 2 multiplied by 10. Question 3. Two identical springs identical to the spring in question 1. It means they have the force of 10 Newton and the extension of it, or fixed, extends at 5 centimeters, are joined in series, connected end to end. It means we have two springs are connected to each other. How far will the combined spring stretches when a force of 10 Newton is applied? How far will the combined spring stretches when a force is applied? When you look at the word how far, this means what they want in the question is the extension of the length. You can use two laws. You can use Hooke's law by assuming these springs are typical or ideal, or you can use this law. The constant equals to force over extension. By going back to the information that we obtained from question 1, we've known that the value of the constant is 2 by dividing 10 by 5. Now, how far will the combined spring stretch when a force of 10 is applied? So we're going to say the 2 equals 10 over the extension. The extension, if there is one spring, is 5. However, there are two identical springs connected to each other, so we need to multiply the extension by 2. If you can do the question 4 as homework on your own, please do. How does the behavior of a steel rod compare to the ideal spring? If you can look at this picture, this is what a steel rod looks like. It looks like a cylindrical or a stretched cylindrical shape that has the surface of a circle. It's very important to note that the surface of it is a circular form. Place steel rod in an instrument. Instrument is this machine, okay? This one. Similar experiments can be done with bones, tendons, wood, etc. So basically, any cylindrical shape, this experiment can be done with. Okay, as we said, as a cylindrical shape is or a straight cylindrical shape is the shape of a steel rod, bone, tendons, etc. And it also depends on the thickness of the rod. We have two uh, important words here, which are the stress and the strain. The stress is the force per unit cross section of material area in Newton meter to the power of -2. For a cylindrical rod, the area is pi by radius to the power of 2. So, in short, the stress is the force applied. Okay? The strain is the extension relative to the original length. So, in a spring, when you apply stress or you apply force, you can visibly see or it's visualized that the extension or the length of of the spring will change. Okay, it will increase by stretching and by the physical properties of the spring. However, in the state of a rod shape or the steel rod, you will not notice the visible extension or the length of the string. But if we dig deeper and we look at the molecular changes of the steel rod, okay, there will be some changes applied. Any object, any object in the world that a force will apply upon, it will undergo two two forces or two uh, changes will be placed upon it. The first one is the stress, which is the force per unit. Okay, let's imagine you have a steel rod on a surface. You put a steel rod on a surface, and you apply some type of force over the top of the rod. This rod will undergo two powers on it. The first one is the stress, which is the force of the rod that you applied on the rod. Okay, that will this force of the stress will affect the rod from up to down, and it will press on the rod. Since you have the rod of the steel rod placed on a surface, naturally there will be an opposite force affecting the rod in the opposite direction. And that's why you won't see any visible changes of the rod. Okay? However, it will still undergo a strain, which is extension. As we said before, you will not notice the physical changes in it because the molecule of the steel rod is extremely compact against each other, giving the thick and rigid properties of the rod. If we want to know the value of stress and strain, for the stress, you divide the force over area, okay? And in the case of rod, as I told you, it's very important to know that it has a circular ends. Because it has circular ends, we're going to use the law of area of circles, which is pi multiplied or pi by radius squared. For the strain, we're going to divide extension or the length of the rod or the object that we have over the original length or the original extension. If you look at questions or problems regarding the stress or strain, of course you will need units. The unit for stress is Newton Pascal, okay? However, the strain, it doesn't have any units because when the units of extension are usually by meter or centimeter, and the original length also we measure it by meter, centimeter, inches, and so on. So if you have the extension will have the unit of a meter or let's say a centimeter, and the original length will have the centimeter, then the units will take out each other and the strain will remain unitless. Okay? The strain doesn't have any units. When the rod is being stretched, we can think about tensils. We have two new words which are tensile stress and tensile strain. We can understand the meaning of these two words, tensile stress versus tensile strain, by looking at this diagram. As I mentioned before, you will not notice the physical or the visual changes of the rod that when a force is applied to. So I will not notice the stress nor the strain of it. To understand this further, we can look at this diagram. We have on the x-axis the stress, and the y-axis is the strain. And you have here the points of E, P, A, and D are the forces applied. Number one, elastic deformation. The elastic deformation is from point O, which is 0, to point E. The stress to strain curve, as you can see, is a straight line. The rod behaves elastically, okay, like an ideal spring. Of course, it's imaginative because a rod a rod will never act as a spring, but as we said, imaginative. So O to E, from point O to point E, is a stress-strain curve straight. The rod behaves elastically like an ideal spring. That means if you remove the stress or the force applied to the rod, it returns to the original length at O point.